Hi, this is the first lesson on sequences for Chapter 3. We've decided to split the sequences and series chapter into two parts because it's quite a large chapter. So this is going to be the first of a series of lessons to do with sequences in general. So what are sequences, recurrence relations, and arithmetic series. Later on, there'll be a set of videos to do with geometric series. So you won't be covering the whole of Chapter 3 in this section of videos. So what are sequences? Well, a sequence is a list of values that follow a particular rule, and you've been doing sequences for years now, since primary school probably. Very interesting branch of mathematics. Lots of real-world examples of uses of sequences and sequences that you see around you. Here's just a few, just to show you, how it applies in the real world. So police departments use special algorithms. For example, the PredPol system, the predictive policing system, which helped to decrease crime rates in LA by 12%. That's related to sequencing. Earthquakes follow patterns. So a crime might trigger retaliation, an earthquake might trigger aftershocks. In maths, this is called a self-exciting process, and there are equations that help predict when the next one might happen. In economics and banking and finance, bankers look at historical data, stock prices, interest rates, and currency exchange rates to estimate how financial markets might change in the future. Okay, so there's lots of different examples of how we use sequences to make predictions. There's a very interesting sequence of numbers that you might have heard of called the Fibonacci sequence, which starts 1, 1, 2, 3, 5, 8, 13, etc. So the sequence starts with a 1 and then a 1, and then each term, each subsequent number in the sequence is the sum of the previous two. And there's so much information about the Fibonacci sequence if you look online. It's very interesting. It appears in all around us, in nature, in music, in art, in architecture, which it'll be there but you won't have noticed. A lot of it is related to the spiral that you can see there. So each of that square is 1 by 1, 1 by 1, 2 by 2, 3 by 3, 5 by 5, and so on. And that is called Fibonacci spiral, and that just continues. You'll see that a lot in things related to that, in nature in particular. So here are the spirals, sometimes known as a mystical nautilus. So this is the inside of a sunflower. You can see the spirals there. This is some sort of snail, cloud formations, star formations. In nature, often number of petals on a flower will be a Fibonacci number. So really interesting, especially if you want to do a EPQ on this. Fibonacci has been used in architecture. That's the spiral staircase of the Vatican. Another interesting fact related to Fibonacci is that if you divide each term by the previous term, as you move through the Fibonacci sequence, that number starts converging to an irrational number, 1.618. ... which is known as the golden ratio and is denoted by the letter phi. And shapes that are in the ratio of 1 to 1.618. So rectangles are known as the perfect rectangle. It's considered to embody a perfect proportion between two quantities, and this has been known about for thousands of years. So that's the picture of the Parthenon in Greece. The proportions of that are in the golden ratio. The Taj Mahal in India, the proportions of that are in the golden ratio. So it appears in nature, postcards are often in the golden ratio. It is supposed to be the most aesthetically pleasing rectangle. Fibonacci in art, there's the Mona Lisa. Okay. Leonardo da Vinci was not only an artist, he was also a mathematician. So his painting of the Mona Lisa is in the proportions of the golden ratio. And music, there's awful lot of links to Fibonacci sequence and music. So the sequences are everywhere. This is another spiral. This is related to something that we call a geometric sequence, where each term is multiplied by the previous term to get the next term. That's called the logarithmic spiral, and that's often seen in nature as well. Okay, so what we're going to do, these are what we need to be able to do. We need to be able to deal with arithmetic sequences. We need to be able to deal with geometric sequences. So those two are specific types of sequences. And in this set of videos, we're going to look at arithmetic sequences. And in the next set of videos, we're going to look at geometric sequences. We're also going to look at infinite sequences, finite sequences. We're going to be able to add up terms in sequences, and we're going to be using sequences in real life problems. Okay, so let's start. There are many different sequences of numbers. A list of numbers is a sequence if it follows a pattern or rule. So if we look at these three sequences of numbers, 2, 4, 6, 8, so you can see that to get from one number to the next, we are adding 2, so that's following that rule. The next set of numbers, to get from one to the next, we are multiplying by 2, so that's that rule. And the last one, well, that's, if you look at the difference between each number, it's going up by 5, and then it's going up by 7, and then by 9, and you'll probably know that they are related to the square numbers. Okay, but that's following that particular rule. So each set of numbers, the numbers are in a given order, and there is an obvious rule for obtaining the next number. Okay, such sets of numbers are called sequences, and each member of the set is called a term. Okay, so we can work out each term in a sequence if we know how to get what the rule is to get from one term to the next. So this one, the term to term rule will be +2, and this one will be times 2. This one, a little bit more complicated, and we'll come back to that shortly. Okay, so here's a little bit of notation that you need to know. N is representing the position that the number's in. So this one is in position 1. This one is in position 2, for example. So the letter N denotes the position that each term is in. UN represents the nth term, so the number in the nth position. So if I say U3 is 7. So that is where n is 3. So we can say that U3 equals 7. Okay. So this is our notation. Now you will know from your school days that this is called a linear sequence. So that's what you will have called it at school. And the linear sequence, we know it's linear because it's going up by 2 each time. Okay, so it's going up, it's increasing by a constant, and in this instant, the constant is 2. Now you also know that because you have a linear sequence, you can write down a rule that connects the position that the number is in with each term in the sequence, and that is the nth term. And in this case, the nth term, because it's going up by 2 each time, is 2n. If I do 2 times 1 to get the first term, that's 2, but I need 3, so we need to add 1 to it. That is the nth term, and we denote that by un. Okay, so this is our nth term. So that one, that specific nth term, generates that sequence for different values of n. Okay, so some sequences we know how to get from one term to the next. For other sequences, we can work out how to get from each term from its position. So the term this is the position to term rule. So how the rule that links the position that the number's in, the term to term rule in this case would just be +2. So these are some nth terms. You can see they're not all linear. To work out what the first 5 terms are for each sequence, we're going to work out U1. U1 is going to be when n is 1. So when n is 1, that's going to be 3. U2 is going to be when n is 2. So that's going to be 7. U3 will be when n is 3. 4 times 3 take 1 is 11. U4, 4 times 4 take 1 is 15. U5, 4 times 5 take 1 is 19. Okay, this one is a linear sequence. It's going up by 4 each time. It's related to the 4 times table. This one, U1, if I put 1 in there, I'll get 0. If I put 2 in there, I'll get 3. If I put 3 in there, I'll get 8. 4 squared take 1 is 15. 5 squared take 1 is 24. This is a quadratic sequence. And then this one, if n is 1, 3 to the minus 1 is a third. When n is 2, it's going to be 0. 3 to the 0 is 1. When n is 3, 3 to the 1 is 3. When n is 4, 3 squared is 9. When n is 5, 3 cubed is 27. Okay, so you can see this is being multiplied by 3. Okay, so this is an exponential sequence. Sometimes we call that a geometric sequence, and we'll look at those later on. Okay, so this is how to use the nth term to generate terms in a sequence. So you need to remember that n represents the position. Okay, so I'd like you to pause the video and see if you can figure out what the nth terms are for those 6 sequences. Okay, so the first one, going up by 3 each time, so that's 3n plus 1. The second one is going down by 4 each time, So that's going to be minus 4n plus 10. This one is going up by 3, then by 5, then by 7. So that's related to the square numbers. Now, what you could do once you've figured that out is just write down the square numbers underneath, and you should notice that they are all 1 more than the square numbers. So that's going to be n squared plus 1. This one is going up by 6, and then by 10, and then by 14, which is similar to this. So that's also related to the square numbers. If you write the square numbers underneath, you should notice that each number is twice the square number. So that's 2n squared. This number, to get from here to here, we're timesing by 2. That's times by 2. That's times by 2. So that's going to be, they are basically all powers of 2. Now if I do 2 to the n, if I put 1 in that to get the first term, that would give me 2, but I don't want 2, I want 1. So I need to take 1 off that index. And then this last one, well, the numerators are going up by 2, so that's 2n minus 1. And then the denominators are going up by 2, so that's 2n. Okay, so each of these are the position to term rules. Okay, so here's a problem. Looks a bit weird. It's basically just lots of notation. So it's just testing whether you understand what the notation is. So this is an nth term. un is some constant plus 3 to the n minus 2. And we are told that u3 equals 11. So that means that when n equals 3, un equals 11. So we can use this information to form an equation. So 11 equals c plus 3 to the 3 minus 2. Well, that's just 1, which means c is 8. So we now can say un equals 8 plus 3 to the n minus 2. So now if we want u6, we just need to put 6 in. So it's going to be 3 to the 6 minus 2. Well, that's 3 to the 4, which is 81. 81 plus 8 is 89. Okay. So just a little test on the understanding of what everything means there. Okay, so some of those sequences were linear, some were quadratic, some were not, some were a bit weird. Sometimes we cannot write down a position to term rule, an nth term, because the rule to get from one term to the next is too complicated. All we can do is give a rule for how to get from one term to the next. So we cannot link the value of the term to the position, we can only link it between one term to the next term. And that is what we use a recurrence relation for. So it's another way of describing a sequence using the relationship between the one term and the next. So it says it's particularly useful when it is difficult to find a standard formula for the nth term. So if it's not linear, if it's not quadratic, if it's a weird one like Fibonacci sequence, there is no nth term for the Fibonacci sequence. All we can do is relate one term to the next, or in the Fibonacci sequence, one term to the next two. Okay, so notation for that. Well, we've still got this UN, so we use that to represent each term. But because we are relating it now to the next term, we use UN plus 1. So if UN plus 1 is one term, then UN represents the previous term. And an example of what a recurrence relation would look like is this one. So UN plus 1 equals 2UN plus 1, comma, U1 equals 3. So this is the rule, and this is a starting number or a starting term. We always have to have both. So the rule says that each term is the previous term times by 2, add 1. And the starting number, the first term, is a 3. So if we had to generate this sequence, the first term would be a 3. To get the next term, so this is U1, U2 is going to be 2 times U1 plus 1. So 2 times 3 plus 1 is 7. U3 will be 2 lots of U2 plus 1. So U3 will be 2 lots of 7 plus 1. U4 will be 2 lots of U3 plus 1. U5 will be 2 lots of U4 plus 1, and so on. So we've got each term is 2 lots of the previous term plus 1. Don't get too bogged down with this notation, just know that it's a term and the previous term. Okay, and you can see this is not a linear sequence, it's going up by 4, then by 8, then by 16. It's not a quadratic sequence either, it's a funny one. Okay, so it would be very difficult to find an nth term for this sequence, therefore we write down the rule as a term-to-term rule, or in other words, a recurrence relation. One thing I probably should mention is that it does need to have a starting value. It's really important when you write down a recurrence relation, or you are given a recurrence relation, that you have a starting value, because if that was different, if U1 was, let's say, 5, then that would generate a different sequence. 2 times that plus 1, 2 times that plus 1, 2 times that plus 1, and so on. Okay, so there will be lots of sequences that follow that rule, but the only one that's going to give us that is if we are told that starting value. So you must always give a starting value, otherwise you don't know where to begin. Okay, I'd like you to pause the video and write down the first 5 terms of the sequence. The first term is given to you. Okay, so this one is 5. Each term is the previous term plus 2. So the previous term plus 2, the previous term plus 2, plus 2, plus 2. So this one is a recurrence relation that is describing a linear sequence. This one starts with 1. Each term is the previous term times 3, times 3, times 3, times 3, times 3. 81. Okay, this one is a geometric sequence. This one starts at 20, 0.5 lots of the previous term, so half the previous term plus 2, so half of that plus 2, 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 and so on. Okay, so that's what you should have got. Okay, now I'd like to see if you can write down what the recurrence relation is for each of these sequences. So pause the video again. Okay, so this one is going up by 3, by 3, by 3. So each term is the previous term plus 3, where the first term is a 4. This one times 2, times 2, times 2. So each term is the previous term times 2, where the first term is a 1. This one, well, it's difficult to say by looking at what it's going up by. 2, 4, 8. So it's more complicated than that. If you multiply this one by 2 and then add 1, you get 3. Times by 2, add 1, times by 2, add 1. So each term is the previous term times by 2 plus 1, where the first one is a 1. Now this one, this is Fibonacci's sequence. I've already mentioned the fact that each term is the sum of the two previous terms. Well, to write that down, we need to write un plus 2 is un plus 1 plus un, where un is 1 and where un plus 1 is 1. So a bit of a funny one, that, but we can still express Fibonacci's sequence as the sum of the two previous terms where the first two terms are 1. Okay, so a bit of a funny one, but that's the way of describing Fibonacci's sequence. Okay, now there's a bit of terminology to do with describing a sequence that you might be asked. So I'd like to write down the first 4 terms from each sequence. So pause the video, write them down, and then I'll talk to you about how we would describe the type of sequence. So I'll describe what it's doing. Okay, so this one starts off with a 6. Each term is the previous one halved, so that's 3, that's 1.5, that's 0.75, and so on. This one, each term is the previous term squared plus the previous term, so 1 squared plus 1 is 2, 2 squared plus 2 is 6, 6 squared plus 6 is 42, and so on. This one, each term is 1 minus the previous term halved times 2. So the first term is 20. If I halve that and take it away from 1, I get minus 9 times 2 is minus 18. If I halve that, I get 9. I get minus 9 even. 1 minus minus 9 is 10 times 2 is 20. then I'm going to get minus 18 again, and so on. This one, 40 minus 2 times 5 is 30. 40 minus 2 times 30 is minus 20. 40 minus 2 times minus 20 is 80, and so on. That was a bit of a funny one. Okay, this one, as you can see, the numbers are getting smaller. So each term is smaller than the previous term. That is called a decreasing sequence. So each term is smaller than the previous term. This one, each term is getting bigger and bigger and bigger. This is called an increasing sequence. This sequence, well, that's just swinging back and forth between 20 and minus 18. This one is called a periodic sequence. So that one is periodic. And this one, well, this is neither. This is going from negative to positive, going bigger and bigger and bigger. Both negative and positive. So that's neither, none of those. Okay, so you need to be able to describe whether you have a decreasing sequence, an increasing sequence, or a periodic sequence. And that is just the summary for those. So if one term is bigger than the previous term, for all positions, it's increasing. If it's less than the previous term, for all terms, then it's decreasing. And if it's periodic, then the terms repeat in a cycle. Okay? So that's just the summary of that. So you might be asked, once you've written your sequence, to describe what sequence the sequence is. Right, just to finish up, we're going to just do a few problems that involve recurrence relations. So here's the first problem. The sequence minus 4, minus 3, minus 1, 3, 11 is defined by the recurrence relation. Each term is the previous term times by some unknown plus some other unknown. Find the values of A and B. Okay, now we have got two unknowns. That means we're going to have to work out two equations. So in other words, we're looking to solve simultaneous equations. Okay, if we've got two unknowns, then we need two equations. All right, now this is U1, U2, U3, U4, U5. Each term is the previous term times A plus a number. Okay, now we can pick any two pairs of numbers. I'm going to use these two because they're positive. So U5 must be something times by U4 plus B. So I can say that 11 must equal 3 times A plus B. I can also say that U4 must equal A times U3 plus B. So 3 must equal minus A plus B. Okay, that's equation 1. That's equation 2. So if I'm going to write that one underneath there. B is the same, so if I subtract to eliminate the B's, 11 take 3 is 8. 3a subtract minus a is 4a. B's are eliminated, which means a must be 2. And if a equals 2, then b must be 5. Okay, so I could have used any pair of numbers, those two and those two. It doesn't matter. What you've got to understand is what this is saying. Okay, once you've done that, then the rest of it is subbing numbers in to get you two equations. Let's have a look at another one. A sequence has a recurrence relation un plus 1 equals 3 un plus k, where u1 equals 2 and k is a constant. Given u3 is 50, find the value of k. So we've got one unknown, then we're going to need one equation. This is our information, so we're going to have to form an equation with a k in it. Well, we know what u1 is, we know u1 is 2, and we know what u3 is. So we're going to have to use our recurrence relation to figure out something for u3. So if I say u2 is 3 lots of u1 plus k, so u2 is 3 times 2 plus k. u2 is 6 plus k. So that's u2. So now if I say that u3 is u3 lots of u2 plus k. So u3, well, we know what u2 is now. u2 is 6 plus k. So 3 lots of 6 plus k plus k. And we know that that is equal to 50. So here's our equation. 3 lots of 6 plus k must equal 50. That's our equation that we have formed with a k in it. If I just solve this now, 18 plus 3k plus k equals 50. 18 plus 4k equals 50. 4k equals 32, so k is 8. Okay, so if you are given information about one particular term, then you need to use that particular term to form an equation with the unknown in. Okay, here's a couple of little exam questions. Have a go, pause it, have a go and see if you can follow what I've just done in order to work out part A, B and C. It's very similar to the previous question. Okay, so if we just go through the answers for you. So don't be confused by the x, if you just use x instead of u, doesn't make any difference. So x2 is going to be a lots of x1 minus 3, so that's a minus 3, that's part A. Now it's talking about x3 here, so x3 is going to be a lots of x2 minus 3. So x3 is going to be a lots of a minus 3 minus 3. And then if I expand that out, a squared minus 3a minus 3. That's part B. Part C, given that x3 equals 7. So we now know that this equals 7. So we put it equal to 7, then we just have a quadratic that we can factorise. So a minus 5 and a plus 2 in brackets. So that tells us that a can be 5 or a can be minus 2, and those are our answers. Okay, so they might switch letters, doesn't matter, just need to recognise that you've got a recurrence relation. All this is just a constraint, just to say that n has got to be a positive number, because you can't have a negative position. Okay, so remember n is just representing the position that the number's in. Okay, and then here's another one. Again, just have a little go at it. The tricky part is the bit at the bottom. We'll come back to that. Okay, so it says find x2 in terms of p. So each term is the previous term times by p plus the previous term. So x2 is going to be 1 times by p plus 1. So that's p plus 1. x3 is going to be the previous term times by p plus the previous term. So it's the previous term, x2, times by p plus x2. So x3 is p plus 1 times by 2p plus 1. So if I expand that out, 2p squared plus p plus 2p is plus 3p plus 1. And that's that. Given that x3 equals 1, find p. So similar to what we've just done, that's equal to 1. So 2p squared plus 3p plus 1 equals 1. So if I take the 1 off both sides, I'll get 0. There's no constant term, which means I just need one set of brackets. 2p plus 3 equals 0. So either p is 0 or p equals minus 3 halves. Now go back to the question. It says there p is not equal to 0, so we can reject that, and that is our value of p. Okay, so just make sure you read the small print. Okay, p can't be 0, otherwise there won't be a sequence. Okay, now the last part, write down the value of x 2008. Okay, so how are you supposed to work that out? Well, at the moment, we can't see what the sequence is. So the trick here, if they ask you to work out a value of something bonkers like that, you need to know what the sequence looks like. So the sequence, well, the first term is 1. And then the second term is p plus 1. You've just worked out what p is. Well, p is minus 1.5, so minus 1.5 plus 1 is minus 0.5. The third term you can get from here. So if I substitute minus 3 halves into here, I'll get 9 quarters, that's minus 3 halves squared, times by 2, minus 9 halves, 3 lots of minus 3 halves, plus 1. Well, this is 9 halves, so 9 halves minus 9 halves plus 1 just leaves me 1. So that means that the next term, if that term was 1, the next term will be negative 0.5. And so what we have is a periodic sequence. The odd numbered positions are 1. The even numbered positions are negative 0.5. If we want position 2008, well, because that is even, then that is going to be negative 0.5. Okay, so any question like that where it asks something a bit daft, you need to know what the sequence is. So write out the sequence. So any question where you're thinking, how on earth am I supposed to know that? Write out the sequence and all will become clear. Okay, so you should now have had enough examples to have a go at those questions on exercise 3G and 3H. Don't try any of the other ones. I'm doing things slightly out of order. That's the end of this video.